Welcome back to the classroom. Today's topic is the study of voltage breakdown mechanism of zener diode control region. This class builds on what was covered in my previous class. You can find the link to that class in the description. Displayed waveform illustrates the extension of reverse biasing until voltage breakdown occurs. While all PN junctions voltage breakdown, it is essential to recognize that there are two different mechanisms for this breakdown. First one is zener breakdown and second one is avalanche breakdown. In zener breakdown, the breakdown voltage decreases as the temperature of the PN junction rises, whereas in avalanche breakdown, the breakdown voltage increases with an increase in temperature. This waveform displays the typical breakdown characteristics for each type. The determining factor for which breakdown mechanism occurs is the relative concentrations of impurities in the materials that make up the junction. This video is sponsored by Genreviews. When two different resistivity p-type materials are placed against two equal doped low resistivity n-type materials, the depletion region in the low resistivity p-type material will be smaller than that in the high resistivity p-type material. Furthermore, in both cases, only a small portion of the resulting depletion width will extend into the n material if its resistivity is low compared to that of the p-type material. In other words, the depletion region primarily expands into the material with the highest resistivity. Additionally, the electric is also a factor to consider. The electric field in materials with lower resistivity is stronger than in those with a higher resistivity due to higher concentration of ions per unit volume in the less resistive material. Consequently, a junction that creates a high electric field intensity leading to breakdown via the zener mechanism. In contrast, a junction with a wider depletion region, which results in a lower electric field intensity, will undergo breakdown through the avalanche mechanism before reaching the conditions necessary for zener breakdown. The zener mechanism can be qualitatively explained as follows. Since the depletion width is very small, applying a low reverse bias generates an electric field across the depletion region approximately 3 into 10 to the power of 5 volt per centimeter. Such a strong electric field applies a significant force on the valence electron on the silicon atom. The way avalanche breakdown depends on temperature is quite distinct. In this case, the depletion region is wide enough that carriers can collide before completely traversing the area, meaning the depletion region is broader than one mean free path. Consequently, as the temperature rises, increased lattice vibrations reduce the distance a carrier can travel before colliding, necessitating a higher voltage to move it across the depletion region. As previously mentioned, the applied reverse bias leads to a slight moment of intrinsic electrons from the p-type material towards the positively charged n-type material and intrinsic holes from the n-type material towards the negatively charged p-type material, resulting in leakage current. As the applied voltage increases, these electrons and holes gain more speed. Additionally, as these intrinsic particles navigate through the depletion region, they collide with bound electrons. If the applied voltage is low enough that the intrinsic electrons do not reach high velocities, these collisions will drain some energy from the intrinsic particles, affecting their speed. However, if the applied voltage is increased, collisions with valence electrons can impart significant energy to the electrons, allowing them to escape from their covalent bonds. As the temperature rises, the likelihood of low momentum intrinsic particles ionizing the lattice atoms decreases. Higher voltage leads to greater acceleration of these intrinsic particles, resulting in an increase in their average momentum and a higher production of electron-hole pairs. If the voltage is increased sufficiently, The average momentum becomes high enough to generate electron hole pairs, leading to carrier multiplication. Therefore, with rising temperature, the avalanche breaking down voltage also increases. Next is fabrication techniques of zener diode. Introduction. A brief overview of the techniques involved in the production of zener diodes can offer engineers valuable insights for their applications. Understanding how zeners are made enhances the comprehension of their capabilities and limitations. This section outlines the fundamental steps in the fabrication of zener diodes from crystal growth to final testing. Next is zener diode wafer fabrication. The main stages in the production of zener diodes are illustrated in the process flow shown in the figure. It is essential to note that the manufacturing process can differ among various manufacturers and also depends on the specific type of zener diode being produced. These variations are influenced by the required packaging and the desired electrical characteristics. For instance, alloy diffused devices offer excellent low voltage references and low leakage properties but lack the surge handling capacity of diffused diodes. The manufacturing process starts with the growth of high quality silicon crystal. Crystals for on semiconductor zener diodes are produced using the common technique that starts with ultra pure polycrystalline silicon. Initially, the polycrystalline silicon is melted in a non-reactive temperature slightly above its melting point. The precise amount of the desired dopant, such as phosphorus or boron, is then introduced. A high quality seed crystal with the required crystalline orientation is lowered into the molten silicon while rotating. Part of the seed crystal melts into the silicon. The seed is then slowly pulled upward while continuing to rotate, allowing it to cool and collect material from the melt, ultimately forming a single crystal ingot. This method can produce ingots with diameters of several inches. Next is the study of basic fabrication steps in the silicon planet process. After the single crystal silicon ingot is produced, it undergoes testing for doping concentration, levels of unwanted impurities, and minority carrier lifetime. The ingot is then cut into thin, circular wafers. These wafers are chemically attached to eliminate saw damage and polished with progressively finer grits until a smooth, mirror-like surface free of defects is achieved. Following this, the wafers are cleaned and stored in vacuum-sealed carriers to avoid contamination. At this stage, the wafers are prepared for device fabrication. Zener diodes can be produced using various processing methods, including planar processing or mesa etch processing. Most of on semiconductors zener diodes are made using the planar technique as illustrated in figure. The planar process starts with the growth of an ultra-clean protective silicon dioxide passivation layer, typically formed at temperatures between 900 and 1200 degrees Celsius. Once this protective silicon dioxide layer is established, it needs to be selectively removed from the areas where dopant atoms will be added. This is accomplished using photolithographic methods. A light-sensitive solution known as photoresist is applied to the wafer by spinning it on. After drying, a photographic negative or mask is positioned over the wafer. The resist is then exposed to ultraviolet light, which causes its molecules to cross-link or polymerize, making it very rigid. Areas of the wafer shielded by the opaque parts of the mask remain unexposed and are subsequently developed away. The oxide layer is then etched away to create opening where the dopant will be introduced. The remaining resist is removed and the wafers are thoroughly cleaned in preparation for the doping process. Dopants are then applied to the wafer surface using various methods such as aluminum alloy for low voltage devices, ion implantation, spin-on dopants, or chemical vapor deposition. After the dopant is deposited, junctions are formed during a high temperature drive-in process, typically between 1100 and 1250 degrees Celsius. The resulting junction profile is influenced by the background concentration of the initial substrate, the amount of dopant applied to the surface, and the duration and temperature of the drive-in process. This junction profile ultimately determines the electrical properties of the device. Additionally, during the drive-in phase, extra passivation oxide is formed to provide further protection for the devices. After the junction is formed, the wafers undergo a process known as getter processing. This step involves applying high temperatures and slight stress through a high doped phosphosilicate glass layer added to the back of the wafers. This treatment helps any contaminants near the junction to move away from the area, enhancing the reverse leakage characteristics and stability of the device. After the getter process, a second photoresist step is performed to expose the contact area where the anode metallization will be applied. The metal systems used for on-semiconductor zener diodes are based on the specifications of the package. These metal systems are deposited in ultra-clean vacuum chambers using electron beam evaporation techniques. Once the metal is applied, photoresist processing is used to create the desired patterns. The wafers are then lapped to achieve their final thickness, and the cathode metallization is deposited using the same electron beam process. The quality of the wafers is continuously monitored during the manufacturing process through statistical process control methods and detailed microscopic inspections at key stages. Special equipment is employed to handle the wafers, minimizing contamination and preventing any damage. This approach improves the quality and reliability of the devices. After the fabrication process is finished, the wafers undergo electrical probing, inspection, and packaging for shipment to assembly operations. All zener diode products from ON Semiconductor are cut using 100% saw-through techniques that have been rigorously developed to ensure high-quality silicon dies. This is the brief study of voltage breakdown mechanism of zener diode control region. Thank you for watching.